Hello everyone. In this last part of the module on next generation fibers, I will be talking about approaches for design of stimuli responsive fibers. Stimuli sensitive polymers, here the SSP changes from hydrophilic to hydrophobic across the transition temperature. During this, the polymer changes in the solubility. Below the transition temperature, the polymer is soluble, and above the transition temperature, the polymer comes out of the solution or becomes insoluble. But what happens if we have a cross-linked polymer? If we have a cross-linked polymer from the same monomer, then below the transition temperature, the polymer would be in a highly swollen form, kind of a gel form. It would be highly swollen, it would have large amount of water trapped inside the structure, and above the transition temperature, it would release all the water will come out and the polymer will become collapsed. So, these polymers are generally used in the gel form, because in the water soluble form they have very limited applications. But when you have to use something in the gel form, it has several drawbacks. One major drawback is the gels are very flimsy, they have very poor strength, they will break down very easily, and the second thing is they cannot be processed. They cannot be processed because they cannot melt, because they are cross-linked, and they cannot dissolve any solvent. So, how do you process them, right? So, if you are not able to process them when the gels are made and they have poor properties, so you try to make thicker gels, so that they have properties, mechanical properties which can be suitable for the application. But the moment you make thicker dimensions, the response becomes slow, it will swell slowly, it will collapse slowly, and also not only that, the magnitude of response, that means how much will it swell and how much will it collapse, that will also reduce, because the response is a diffusion controlled phenomena. It happens because the water molecules are diffusing in, interacting with the polymer chains, or they are diffusing out. So, this diffusion is a slow phenomena and it is dependent upon the thickness or dimensions of a particular structure. So, when you have thicker structures, they would take much longer to respond, right. So, that is the major limitation, but we can't use them in the soluble form. So, SSPs are interesting materials, but have limited applications in the gel form. First, let us have a look at what kind of applications do SSP gels have. I have been using this word SSP, that is stimuli sensitive polymers. Let me repeat, stimuli sensitive polymers. So, where can these be used? Let us look at that. They have many applications. If you have a SSP gel, it can be used for separation and purification, because it absorbs water. So, you can remove water if it is a contaminant in anything, any organic solvent, you can remove that. It can be used as an artificial muscle, because they change shape and size. It can be used as actuators. It can also be used to release the drug under certain conditions, certain temperature conditions, and if one is able to convert these SSP polymers into textile structures, meaning thin one dimensional structures, then this structure would become an intelligent structure, and this intelligent structure would have much enhanced performance in all these applications, be it drug delivery or actuator or a separation or artificial muscle. So, it is pertinent, important that one should try and convert these stimuli responsive polymers to textile structures to get enhanced properties. So, I will be taking an example of a temperature responsive stimuli sensitive polymer, and will be discussing an approach to make stimuli sensitive fibers which are responsive to temperature, and the same approach can be extended to other polymers as well. So, before we do that, I would like to introduce to you a most popular stimuli sensitive polymer, that is poly-NEPA. Poly-NEPA means poly and isopropyl acrylamide. The structure of this is given over here on the slide. If you see, it is an acrylamide structure in which one hydrogen has been replaced by isopropyl group. This isopropyl group is a hydrophobic moiety, and amide group CONH is a hydrophilic moiety. So, it is actually the balance between this hydrophilic and the hydrophobic groups that decides the transition temperature of the polymer. NEPA has a transition temperature of 34 degrees. That means, at 34 degrees these hydrophilic and hydrophobic interactions they balance, right. At temperatures lower than 34 degrees, hydrophilic interactions are more dominant. So, your polymer will be soluble, or in the gel form it will be in the expanded form or a swollen form, and above 34 degrees this polymer would be in the collapsed form, insoluble form, or the gel will be in the collapsed form. So, the transition temperature is shown by these materials because with rise in temperature above the transition temperature, hydrophilic interactions, that is hydrogen bonding with water gets disturbed and hydrophobic interactions dominate, because when you give heat, the temperature, the hydrogen bonds break. So, that means the interaction with the hydrophilic moiety is over, is removed. So, therefore, the hydrophobic interactions dominate, which does not allow it to swell or dissolve. So, therefore, at higher temperature it either comes out of solution or it collapses. Now, the question arises, can I tune this transition temperature? I need a polymer for using at a temperature of 37 degrees, somewhere very close to the human body temperature. Can I do that? Is it possible? The answer is yes. One can do that either by changing the chemical structure of the monomer itself, so that you are able to change the hydrophilic hydrophobic balance, or the second way is you can use a copolymer. You can use two monomers, one is hydrophilic, one is hydrophobic, so that contributes to the hydrophilic hydrophobic balance. So, we can make fibers from these, but how do we do that? Because gels are not easily processable, we can't process the gels. So, what should we do? So, for doing this, for making temperature sensitive textile, the approach which I am going to discuss is based on the process in which we first synthesize a polymer which is stimuli sensitive, which is temperature sensitive, and it is processable. So, when I say processable, it necessarily has to be a linear polymer, right. So, that means I first make a polymer which is a linear polymer, processable polymer. Then I process it or convert it to a particular shape like a film or a fiber or a coating, and then I stabilize it. The stabilization over here means that I cross-link it in that particular shape. So, I have used the linear polymer, I have used the property of the solubility of the linear polymer to convert it to the shape and then cross-linked it. This approach is very similar to the approach which is used in the case of PVA kind of fibers, right. So, processing into thin shapes, maybe fibers, or coating it onto the textile substrate. I can also coat it onto the textile substrate, so that a thin film or a coating is formed, and then I heat treat it or I cure it, and in that process these coatings become mechanically strong, and all this has to be done in such a manner that the resultant or the cross-link structure retains its temperature sensitivity. That is very important. I have to ensure that the process that I do is such that the final structure retains its temperature sensitive property. So, this is the fundamental approach which we have used in developing temperature responsive fibers, which I am going to share with you. One can engineer the structure of this by choosing two different monomers, as I said. You can choose a hydrophilic monomer like acrylamide and hydrophobic monomer, which is a substituted N-substituted acrylamide, that is N-tertiary butyl acrylamide. So, hydrophilic and hydrophobic monomers. So, the copolymerization can be carried out by choosing different proportions of these polymers. So, at about ratio of 73 to 27 acrylamide to N-tertiary butyl acrylamide, one is able to obtain a copolymer, a random copolymer, which has a transition temperature of 37 degrees. Transition temperature is also known as LCST, that is lower critical solution temperature in the case of linear polymers. So, it is about 37 degrees. So, that is at 37 degrees the hydrophilic and hydrophobic interactions, they balance. Now, we have chosen hydrophilic component acrylamide also as a reactive site. If you recall, in my last slide I said we need to stabilize this structure, that means we need to cross-link these structures. So, here the amino group, the NH2 group of acrylamide, which is weakly basic, it has been used as a reactive or a active group for stabilizing these fibers. So, the next step in processing is one can make spinning of the fibers from this linear polymer which has been made, and then convert it into fibers, stabilize them, and these two structures can be used as intelligent textile applications. So, if I make a solution of this particular polymer in a suitable solvent with a cross linking agent like polycarboxylic acid and any catalyst which will help in cross linking reaction, I can solution spin these fibers. The fibers which are spun pass through the coagulation bath, they get coagulated, they can be drawn and subsequently they can be dried at 100 degree centigrade and cured for a very short while at 160 degree centigrade to stabilize the fibers. What will happen at 165 degree centigrade? At 60 degree centigrade, the stabilization would occur because of the reaction of polycarboxylic acid additives which are used as a cross linking agent with the amide groups, the NH2 of the amide group, and this will give a insoluble structure which will not dissolve in water, but it is in the form of a fiber. I can also change the extent of cross linking. I can use different levels of cross linking. For example, here I am demonstrating two levels. Level 1 shows lower degree of cross linking, means less amount of additive has been used, and level 3 shows higher amount of cross linking. So, the fiber which is made from this, in the dry state, it has a diameter of about 27 microns, and if I put the same fiber at 80 degree centigrade in water, it remains in the same shape. It is stable, it does not dissolve, the dimensions remain the same, because it is at a temperature which is above the transition temperature. The transition temperature is about 37 degrees for this particular material. And now, if I take out this fiber, put it in another water bath which is at 6 degrees centigrade, which is much lower than the transition temperature, what will happen? The fiber swells, it swells to 270 microns, and importantly, please notice that it shows an anisotropic change in dimensions. Anisotropic change in dimensions means that there is a greater change in diameter compared to the length. And also, if I look at the transition change happens within 3 to 4 degrees. That means, if 37 degrees is the transition temperature, the moment I reach about 37 degrees, between 37 to 34 degrees, the fiber would collapse suddenly. And also notice that the change is very high. There is a 178% change in the volume of the fiber. So, if I look at the transition temperature, as I had mentioned, the transition is pretty sharp. It happens within 3 to 4 degrees. There is a sudden drop in the swelling behavior of the fiber, and also please notice when the degree of cross linking is low at level 1, the swelling is more, right. When the degree of cross linking is more at level 3, the fiber swells to a lower degree, because now the structure has changed, it has got higher cross linking. So, it has got less number of hydrophilic groups which are present. So, it also reduces the extent of swelling. Importantly, when you change it from high temperature to low temperature to high temperature, you do not observe any hysteresis. It follows the same path, which is very important for any application. Looking at how fast this transition occurs, if I have a fiber, then this transition occurs in a time less than 20 seconds. 20 seconds, that means almost 80% of the change occurs within 20 seconds and it swells. And if I change to the lower temperature, to the higher temperature, then the change is almost spontaneous, instantaneous. The fiber will collapse immediately within a fraction of a second. So, this shows that the transition is very fast, significantly fast transition. If I have over here a disc shaped material and I look at the transition of that, it actually takes pretty long, it takes few hours to swell, whereas here the transition is happening within a matter of few seconds. Not only this, if I look at the change in shape and the cyclability behavior of this material, which is shown in this slide. So, how is this experiment done? That means the 0 cycle means the fiber has just been produced. Okay. So, what you notice is 0 cycle dry fiber, when I put it in water at 80 degrees, it will swell, but it does not swell to maximum degree, it swells to some degree, intermediate level, and then I bring it back to a higher temperature. It will come back to a particular position. The first cycle basically helps to condition the fiber, because I have heat treated it at 160 degrees, I have cured it. So, the fiber has lost all its moisture. So, it takes time to condition, but after the first cycle, if I see, you will notice that the change is pretty high. It is almost 272 times the volume change, right. And the next cycle, heating cycle, it comes down, cooling again it goes up, heating comes down. So, again and again in repeated cycling, you see the same behavior is observed and the fiber does not lose its integrity. It has got high enough mechanical properties that it is able to sustain this change in many cycles. So, which further you would also notice that if I draw the fiber to different draw ratios, then also the morphology of fiber is also changing, the shape changing behavior of the fiber. The higher the draw ratio, I will get higher swelling in the diameter. If I have lower draw ratio, the extent of swelling will be lower. So, that means the morphology can also be tuned depending upon what kind of shape changing behavior is expected for any particular end application. As I was telling you before, this fiber, if I look at the swelling behavior and response time of this fiber with a film sample or a hydrogel sample, you will be surprised to see that fiber of a diameter 27 micron swells to 17,800%, while a film of much lower thickness, that is 10 micron, only swells to 3000%. Whereas, a hydrogel of 2 mm disc, if I take, it swells only to 490. And if I look at the time that it takes, it would take for 50% change, the fiber takes less than 5 seconds. The film of 10 micron takes about 30 seconds, and if I look at the disc, it takes 600 seconds. So, that means the diffusion controlled phenomena occurs better as you have unique directional structure like fibers. The mechanical properties of the fibers were also much superior to the films and the hydrogels. Finally, I would like to say that the shape changing stimuli sensitive fibers discussed over here show sharper response, faster response, that means they are very quick. The magnitude of response is higher, as we have seen in the last slide, right. We looked at the values in comparison to the film and with the disc, and they also had excellent reversibility and stability. That means, in many cycles it would go in the same manner, increase, decrease without losing its mechanical integrity. And anisotropic change in the dimension can also be tuned by using morphological considerations such as orientation, etc. So, this approach which we have discussed, this hypothesis or this approach can also be extended for designing of other stimulus responsive fibers, such as fibers which are responsive to pH or which are responsive to any other kind of response. Only thing is, in each case you will have to choose a suitable monomer or a suitable chemical, so that the material can respond to that particular stimuli. So, I can say in this module on next generation fibers, we have learnt what are the next generation fibers, how are they different from the commodity fibers which we use for apparel applications, and what are the strategies to design them, what are the fundamental approaches to design them. We have learnt about two different approaches by examples of PE gel fiber, and second one, which one was that? By using rigid rod materials, and then we went further on to the next approach, which was for stimuli responsive fibers or the functional fibers or the fibers which can respond to the environment and can give us additional function in addition to the normal textile properties, right. I hope I have been able to explain these approaches, and you will be able to utilize this knowledge to create more such structures which can either give you the tailor made properties or response to a particular stimuli. I will be sharing in the non-video content, I will be sharing some information on pH responsive fibers, and I expect and hope that you all will be able to read that, comprehend it, understand it and utilize it. I would like to use that material as an assignment material for you people to study it as a self-study component in this particular course. Thank you.